Well, hello everyone. We will just continue the solution of some of the problems in the exam 3. So now we have a situation as shown here. Two megaphones at distance of 499. This means, let me see. So there is a megaphone here and megaphone there. And its distance is about 4.99 meter. And then there is a listener. So listener, and then its position is about this. Okay. And the speed of sound is given. Velocity is given. Sound velocity is given. And what is the lowest frequency at which constructive interference occurs? Okay. So we need to figure out there should be two sound waves. One is coming from this, and the other one is coming from that. And then for two-wave interference, the only factor you could think about is a phase difference. Phase difference is the uttermost important things because you are going to add two waves, and then the phase difference, let's say A sine K X1, let's say R1 T plus A sine K R2 minus omega T. So note that in this case, omega is exactly same, A is exactly same. They are in phase, no phase difference. And then you have to do this trigonometric equation, and you will end up with this factor, which is the phase difference. And then it should be compared with m lambda. So the phase difference is multiple over lambda, then it is a constructive. But if delta L is given by half lambda over times m, then it is a destructive. So m lambda, if you just plug in, this is a k, instead sine kx minus omega t here. So k should be multiplied times lambda over 2 pi. So that if you just lambda over 2 pi, and then you can see that lambda goes away, m times 2 pi with the sign value, with the sign is, I'm sorry, so cosine, this one, then you always 1. Okay, so that is the important case of what is happening. And then in the lowest frequency corresponds to smallest positive m, such that L becomes the delta R. And then once you know the wavelengths, you can find out the frequency by utilizing this requirement. Every wave should satisfy this one. F lambda F. So V. And then from this, V is given, delta R is now known, and then you can find out the frequency for the first, the lowest frequency that satisfies the constructive interference. An animal emits on echolocation waves. Let me just try. Okay, so animal emits on echolocation waves. Oops. And how long does it take for the echolocation wave to make a round trip between an animal and the object? Echolocation is that it emits a sound and then it reflects back. Okay, that kind of thing. So usually it is done by the bats, right? So now let's use some of the things we are going to have it. So we are going to assume that it is in the liquid. So for example, dolphin or a whale or some other animals, sea animals can emit a certain sound, and then it listen to the reflections, okay? And then note that this is the liquid, and then we have to remember the velocity of the sound in the liquid is given by this one. Okay, so here B is the bulk modulus, and seawater density is given. Okay, so that we can find out in the seawater velocity, sound velocity is about this. And now what it's going to do is that because the wave goes to the obstacle and the back, so we have a distance is already known, is this one. And then the time for the round trip is very simple. Distance divided by the velocity for the waves. And then we can get the answer. So this problem is a little bit tricky, but basically it is based upon this relationship. So string, we have a tension and linear mass density. Linear mass density is the starting point. But the variation here is that cross-sectional area is changing as a function of x. So in other words, it starts with a certain area and then it's increasing as a function of x. This area is given by this one. Okay, then we have to think about closely. What is given here is the linear mass density. Linear mass density means is a gram or gram per or a kilogram per meter. Okay, kilogram per meter is required. And then what we are given is the volume density, kilogram per meter cubic. And then we have an area, which is the meter square. In order to get the kilogram per meter from the known values, then we note that rho times AX will give us linear mass density. This is the kilogram meter cubic times meter square, and then it is kilogram per meter. So this is what we have to use for calculating the speed of the wave along the string. That means its speed is actually dependent on x. Okay. And then the question is, determine the time it takes for transverse pulse in the string moving back and forth from one end to the other. Okay, so that's the answer. So here we have to go back to kinematics. Okay. So what we have to deal with here is that Vx is given by dx over dt. Okay. And then if you just change it, dt becomes dx over vx. So if you take the integral, then this becomes a t, and then this is what we have to have. It starts from the 0 to length L, okay? And then v-axis is nothing but speed is given by this one. And then we can get the this integral. Okay. And then by changing the variable, this integral can be changed into this, and then we can get the numerical value. Okay, and then you can find out t. Now, the tension in a thin cable, once again, it is tension is given here, and mass is given, the length is given. And then what we need to look up is the tension over linear mass density. And for the given mass and the length, we can find out the linear mass density and then just plug in, and then we can find the velocity. And then we note that this velocity, due to the wind in the air, the cable is vibrating and produces a standing wave at 2 times its fundamental frequency. So what is the frequency of the hum that is produced? So first thing is that we found out that the wave of the string, the wave speed on the string, and then we have to think about the situations. So fundamental frequency here in this case is fixed, so that L. So this L is same as lambda over 2 over fundamental frequency. And then what we have to lambda becomes 2L, right? And then we are using F times lambda is velocity. It's always true. So for the F1, lambda 1 goes like this, and the F1 is lambda 1 is 2L, so that we just put the 2L here. And then this is the fundamental frequency. Frequency of the hum, or second harmonic, is F is 2 times F1. And then this is the second harmonic, you can get the frequency. So in this problem, you first figure out velocity. And then from the fixed boundary, you get lambda is given by 2L. And then from this, you get the frequency 1. And the 2F1 is what we need to find out. Okay. And transverse harmonic wave, your amplitude and the wavelength is given. And from the left to the right, along a long horizontal stretch string with a speed of 29 meters per second. Take the origin at the left end of the undisturbed string at time t equal to 0. The left end of the string has its maximum upward displacement. And we need to find out that the transverse displacement of a particle 1.4 meter to the right of the origin at time t. So here is the situation. So here is the x equal to 0. X equal to, let's say, 1.4 meter. And then initial condition was this. Here, its maximum upward displacement. That means it goes like this. Okay, so it is maximum here. So amplitude here is given A, wavelength is given, and wave speed is also given. Okay, and the wave is traveling from left to right. At t equal to 0, the left hand, x equal to 0 has a maximum upward displacement. So let's assume that traveling wave along the positive x direction is given by cosine kx minus omega t plus phi. Phi could be arbitrary number, but in this case, we are going to set that maximum upward displacement at x equal to 0 and at t equal to 0 means at x equal to 0 and t equal to 0, then it is plus a upward, okay? And its extremum, you can see that if that's the case, the derivative should be 0. So we have two conditions. X equal to 0 and t equal to 0, we get A. And x equal to 0 and t equal to 0, the variation of the y as a function of t is 0. Okay. So from this, what we now know is that we can we can find out the phi. So in order to get this one, then we get phi equal to 0. And then it satisfies all the conditions. So we have this wave. This is what we have. And then in this case, we need to find out what the k is and what the omega is. K could be found by the 2 pi over lambda. Lambda is given. And omega can be found from the v times k. So v is given, right? V is given, and now lambda is given. And then we can find out omega. So that we now know k, we now know omega, okay? And then we can find out that what the A is already given, so that for x equal to 1.4 meter and the t equal to this seconds, note that our wave is function of x and t. So you need to plug in both x and t here to find out the value, okay? And then you get this value, okay? So in this problem, what has happened here is that if you go back, so first thing is that you start with the arbitrary cosine function, and then the initial condition, initial at t equal to 0 and x equal to 0, the condition says that it is a maximum upward. Then by the properties of a cosine, you get this requirement and also this requirement, okay? And then by utilizing these two requirements, we note that phi should be 0. Otherwise, it is not giving you the boundary condition. And then our wave is known. And from the given condition for the lambda, we can find out k. And from the k and velocity, we can find omega. And then all the constants are known. And what we need to do is to plug in x and t value for function over y, x, and t. So here the problem is given like this. String length is given. String mass is given. Speed of sound in the air is given like this. When the string vibrates in its second overtone means it's a third harmonic. So n equal 1 is fundamental, n equal 2 is first overtone, n equals 3 is the third harmonic, okay? So So the second overtone has the wavelengths is known, okay? And then what we need to do is that the frequency of a sound produced in the second overtone, the frequency is given by this one. So all of them are given, okay? And then you can find the frequency. And then the F3 is actually 3 times F1. So its fundamental frequency is F3 divided by 3. So this is the frequency you want to find out. And this is a little bit complicated problem. It is combining the wave and equilibrium, mechanical equilibrium. So now let's try to think about what is given. So we have a wire and there's a pivot, and this uh, 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 this pole is in the case of a gravitational case, you have a G, mg, mg. Okay, so that we have we need to think about the cases. So here is the tension toward this case. Of course, tension toward this case. Okay. And then it is not rotating. Then this is the pivot. You can move back and forth like this. And then what it means is that we have two force. One is due to the tension, and the other one is the weight. Weight, okay, or W. And then torque from the wire here. The distance is LP. So you can find out that this angle and this angle is the same, so that torque is given by T times LP sine theta. Okay, so here is the R T. And it is given by tau is R T sine theta. Angle between them is actually theta. Okay, theta. So this is the torque from the wire, and then at the same time you have a center of mass at the middle point. Yeah, and then weight. And then also it is going to give you torque. But note that wire will turn try to turn in these directions, but gravitation will turn this whole thing into these directions. So tension will give you torque from the wire is the counterclockwise, and torque from the post weight is the clockwise. Okay. And then what we need to do is that because this is in an equilibrium, we have this relationship. So by doing this, so we can find out tension in this wire. Okay. And then we get this tension. And then once we know the tension, then we can find out the velocity of a wave of the dead string given by this formula. Tension is already known, and then we need to find out the linear mass density, which is mass divided by the length of the wire. And then we get this one. And then furthermore, we find out the velocity, and then we need to find out the 6 harmonics. N equals 3, we have if it is fixed at both ends, something like this is going to happen. This is a fundamental, and this one, something. Let's go on and on for n equals 6. Okay, so note that both ends are fixed. And in this case, it satisfies this relationship because it is here L. Now, in this case, L is now lambda over 2. And in this case, L is lambda. L is 3 times 2 over lambda, etc., etc. So that our wavelength would be this one. Okay, so over lambda n. And then we need to find out 6 harmonic. So you need to plug the 6 here. And then we can find out what it is. Okay, and then you can find out the value of the frequency. So in this case, the first thing is that find out the tension in the wire. We did it by using the static equilibrium. That means no net torque should be 0. Okay, that is the starting point. And then once you find out the tension, then you can find out the velocity. And if once we find out the velocity, and then we know that the fixed end has a certain wavelength, and then we can find out the frequency. Okay. So now this is a little bit similar to previous case. So what we need to do is that we have a two vertical wires. This is A and B. So note that those are fixed. Yeah. But if you note that the center of gravity or center of mass is not exactly at the middle, but is 1/3 of the way. So, so this is the center of mass located. And then because of that, you will find out that tension in TA and TB will be different. Okay. And then if the TA and TB is different, then obviously the velocity will be different. Okay. So now let's try to find out what are the tension here. So, so here is that tension is upward. Force should be same as downward force, the net force. And then we have a torque. Force should be 0. So because it is equilibrium, so net force should be 0 and the net torque should be 0. So now let's take this as an origin. Yeah. And then this tension B is giving you this torque, and this weight will give you opposite rotational case. The TB will try to rotate in this way, and the W will give you rotation this way, so that it is opposite direction, so that you have a minus sign. And this is the torque. And then in order to find out TA and TB, we have two equations, equation 1 and equation 2. Then we can find out TA and TB, two unknowns. So we find out TA, TB. And then once we reach this conclusion, and then we could come up with the velocity, which is given by the velocity of a wave over string or wire with the tension T is given by this one. And then we have this TA, TB is included. Note that our linear mass density for two wires are identical, so that the velocity will be different. And then the time travel from here to L is given by L divided by the VA, L divided by the VB, and then we get TAA, TB. And time delay between arrival is given by this one. So in this case, once again, by utilizing mechanical equilibrium, we find out the tension of two strings, TA and TB. And once we find out the TA and TB, we find out the velocity. And then from the velocity, we can find out the time for the wave to reach at the end, okay? And then we can find out the time delay. So now we have so uniform cylindrical wave, still wire, is fixed at both ends. Note that it's fixed at both ends. So this is the situations. And two, what tension must it be just adjusted so that the vibrating in first overtone, so that means n equal 2, it produced a note of a frequency 439 Hertz. Assume that it stretches an insignificant amount, and then still is given by this one. So wave speed for the first tone is we need to figure out we need to find out what the tension is, and then from the given, the frequency is given, okay, and the Fn is given by this one for fixed end. Okay, anyway, this is the wavelength of this one. And then for the first overtone, we just plug in n equal to 2 here. And then we get the velocity. Okay. So once we know the velocity of the dead wave, then it's going to be easy. So once we know the velocity, we can find out what the t is. Okay. So this is the, it's okay. Once again, you need to understand what is the wavelength or frequency for the given string that is fixed at both ends, and that is this formula. And from this formula, we get the frequency, and then frequency is given by this velocity, and then we can find out what the velocity is. Okay. And then once we know the velocity, and we can find out the tension. This is the combination of the Doppler effect and the beating. So now a man walks down a long hall carrying a tuning fork vibrating at this frequency. So the sound reflects from the closed end of the wall, a hole. If the man hears 3 beats per second, how fast is the man walking? Use the velocity of the sound is this one. So folk velocity is this one. Speed of sound is this one. Heard beating frequency is 3 hertz. And we want to find out the velocity of this man. So direct sound, if we set that this is F0, okay. And then what is going to happen here is that the moving source, the man is carrying the fork, that means it's the source is moving, so that we have to use this one, okay. And then it's moving toward the stationary wall, and the frequency at wall will be this one. And the wall radiates as a stationary source with the frequency f wall, and the man moving receives this reflected wall. Note that we have this one. So you have to understand what is happening. So here is the someone, and it generates a sound while it is moving with the U, and then it hits the wall, and then it reflects back. So at the wall works as a kind of a listener, and then at the wall, you get the frequency given by this one. And this works as a kind of a original frequency. And we note that the listener here is now it is the listener. The role has changed. It's moving, and then you get the plus B. Okay. So that you will get this relationship after all. And the beating frequency is that between the reflected and the direct beam. Okay. And then this is the what we get. And then as a result, you will have this one. If we have a beating frequency is 3, and then we can get the what is U is. So the result is a little bit complex, but basically, if there is a beating, that means there is a 2 frequency. The question is, what are those 2 frequencies are? And the first frequency is sound frequency from the fork that is carried by this person. And then second frequency is the frequency reflected at the wall and heard by the observer. Okay. So there's a twofold Doppler effect. This is the first Doppler effect, and this is the second, and this is the net. Okay. And then we have to remember that the beating frequency is the frequency difference. And then we have to plug in the right numbers, and then we can get the numerical value. I think that this would be okay. An organ pipe has 2 successive harmonics with the frequency of 555 hertz and 925 hertz. What is the length of the pipe? Speed of sound in air is given. So now for an organ, it could be either open, open, or open, closed. And successive allowed harmonics are equally spaced by the delta F is given by this one. If you are not so sure, you need to go back to our lecture, and you'll see that successive, so F1, F2, F3, so Fn plus 1. Then what it means is that Fn plus 1 minus Fn is always the same, V over 2L. Okay? And then we find out delta F is given by this value. Note that this is one of the high frequency and the next low frequency. And then this is going to be this one, so that we can find out what the L is. The sound from the trumpet radiates uniformly in all directions at a distance of 7 meters from the trumpet. The sound intensity level is 70 dB. What is the pressure amplitude at distances? At this distance? So we have to think about the conversion of the decibel into pressure amplitude. Okay, so that's the thing we need to find out. So first thing is that convert a decibel to the intensity, and decibel is given by 10 times log 10 I over 0. So in this case, we get this one, and then I0 is here, and then decibel beta is 70. And if you plug in, then you get this intensity. And for a sinusoidal sound wave, we get this relationship. Intensity is given by pressure, amplitude, and then we want to find out this one, and then it is given in this formula. And then if you just plug in the numbers correctly, then you end up with this. So it's a kind of a conversion problem. So first thing is that you need to convert the decibel into intensity. And then the intensity is correlated to the pressure amplitude. Okay? And then we can get the what we wanted to find out. And bat flies toward the wall, emitting a steady sound of frequency of 2.1 kilohertz. This bat hears its own sound, plus the sound reflected by the wall. How fast should the bat fly in order to hear the bit frequency of 8 hertz? So we have a source frequency is given by this one, speed of sound is given one, and we have a beating frequency of 8 hertz, and so we have a F0, and as we have seen before, we have a bat is moving the velocity, and then there will be two Doppler effect. One is at the wall, it will have a frequency given by this one. The bat is moving, so that you will have this denominator. At the reflections, the bat will hear the reflected by this one, so that the overall frequency the bat will hear is this one. And now it's time to think about the beating frequency is reflected minus direct, and then it's given by this one. And then Fe is the 8 hertz. Okay, and then from this you can find out U. And since V is given, velocity of the sound. Okay, and this is the similar to what we have observed. Yeah, in this problem 82, problem 82. And 93 is exactly the same. Now, this is the supersonic problem. Okay. On a clear day, a person sees a jet plane flying overhead, flying at a constant altitude over 8 kilometers. The person hears the sonic boom at time 9.9 seconds after the plane passes directly overhead. So what is happening here is that this is the 8 kilometer. So plane is moving. And then you are here. Okay. So h is given by this. Delay after plane passes overhead from here to here is about 0.9 second. And the plane speed is not known. We need to figure it out. So what is happening here is that steady levels of supersonic flight observer. Here is the boom when the aircraft's Mach cone, this cone, passes them. Okay, here is it passes them. Okay. So let's assume that this cone is passing through this observer. And mu be the Mach angle, mu. And then what is happening here is sine mu is given by v over u. This is the definition of a Mach angle. And in this case, in the case of a mu, tangent hyperbolic is tangent mu is given by mu x h over x. Okay. And the plane was directly overhead at t equals 0 after time t is horizontally at u. And then you want to find out what are the things. And then you can find out from the trigonometric relationship. So sine u is given by v over u. That this is the what we have. And the important thing is this one. This x is actually given by plane velocity times t. And everything is set up such that we need to find out what u is, okay? And from the Mach angle, tangent mu, sine u over cosine mu, and then it is given by this relationship. Okay. Sine u is u over v. Cosine is 1 minus sine square root. So this is what we have. Okay. And then tangent mu angle is given in terms of v and u. And set for equation 4 equal to 2 with x equal to ut. So we get the equation, two equations for the tangent mu in terms of a position and in terms of a velocity. Tangent mu in terms of a velocity and the tangent mu in terms of a position. Okay. And what we need to find out is V and H is known. We will want to find out what the U is. And then after certain calculations, and you will find out U in terms of all the known values. And then you can find out U. So here is the situation is that you start with the Mach angle sine mu, and then you correlate them with the trigonometry in space, so given by h and x. So that this is the trigonometric relationship for in terms of velocity v and u. And now it is another thing is that this angle satisfy h and x. Okay, and then v h a x is already given, so that we need to find out u, and that is equate this tangent mu for velocity and its position, and then we can find out one equation for one known u, and you can find out u. And uniform 150 Newton bar is supported horizontally by two identical wires A and B, and small 185 Newton cube lead is placed 3/4 of the way from A to B. And then this is okay. So the wire are each this is the 56 meter long. Okay. And then if both of them are simultaneously plucked so that its strings will vibrate, okay? At the center, what is the frequency of the beats that they will produce? So because of it's not symmetric, so that tension in TA and TB, TA and TB is not going to the same. So that we have a velocity is not going to be the same. And then for the same material, you will have a frequency is not going to be the same. So that we have a beating. This is the beating, okay? That's the logic. And in order to find out the tension, so note that this is a string. So in order to find out the velocity, V is given by, right? So you need to find out the tension in this case. Once again, we are utilizing the mechanical equilibrium. Okay, so here is the uh, take upward reactions is the RA and RB. This is the RA. Or you can say that it's the TA or TB. Okay, so you can say that it's the TA and TB. It's going to be the same as bar weight and this cube weight. This is upward force, and this is downward force. And then we need to think about, well, so at some point it is changing to the tension. Well, but we have to think about TA. Let's say this is RA. It's going to RB. And then let's take the weight x at its midpoint. So weight and cube. Yeah, okay. So what is going to happen here is that let's take it as A is the rotation center. So that everything for the RA is gone because it is passing through this center of rotation. It does not play any role. What is playing role is that this weight W, WC, and RB. So RB is from here to here is the L. And then this is the weight at the center, and it is a cube at the 3/4 of the length. Okay, this should be 0. Note that RB is moving these directions, and the W and WC is moving these directions, so they are in opposite sign. So RB is given by this one. RA is given by this one. We have two equations. Equation 1 and 2 will give you R and RB, which is same as TA and TB. And then once the tension is given, the next thing is to try to find the velocity by taking the linear mass density from this one. And then this is what we have. This is the velocity. Okay. And then for stretched string fixed at both ends, the fundamental frequency becomes like this. Frequency like this. Note that. No, that's one. We have a string length, and they are fixed at both ends. That means, and then this is Ls becomes half over lambda. Okay. So because of that, you end up with this little relationship. F times lambda is your velocity. Lambda in this case 2Ls, so that F becomes F times 2Ls becomes velocity, which is T over mu. And then F is given by 2Ls T over mu. Okay, that's the things. So we have a FA for TA, FB for TB. It's because TA and TB is not equal, you end up with the beating, FB minus FA. Okay, so that's it. So this is the more or less similar to what we have done before. So you calculate the tension from the mechanical equilibrium. So you could have these cases or this case or this case. Okay. So everything is you have all the force should be 0 and all the torque should be 0. That is the mechanical equilibrium. And from this requirement, you can calculate the tension on the wire like this. Or that. And then once you calculate the tension, then you can find the velocity. And then for the fixed boundary condition for the string, then you can find out what is the wavelength is. And then we have a very important relationship between the frequency and the wavelengths. So this is the fundamental. And the velocity is given by square root T over mu. Okay. Okay, that's it. I hope you could have a good exam tomorrow.